Imagine shrinking a wire down to a scale so small that its diameter is measured in nanometers, just billionths of a meter. So small that electrons moving through it begin to behave not just like particles, but also like waves. This is the realm of 1D materials, where nanowires and quantum wires unlock properties that simply do not exist in everyday materials. These ultra-thin structures are not just miniaturized versions of ordinary wires. They follow the strange and powerful rules of quantum mechanics, and their potential applications range from next-generation electronics to quantum computing and advanced sensors. What makes these 1D materials so special? In simple terms, when you reduce a material's dimensions to near atomic scales in 2 out of 3 spatial directions, keeping it extended in only 1, you drastically change the way electrons and other quasi-particles behave. In bulk materials, electrons can move freely in all directions. But in a nanowire or quantum wire, their movement is confined to just one direction, like cars stuck on a single-lane road. This quantum confinement leads to discrete energy levels, enhanced carrier mobility, and in some cases, ballistic transport, where electrons can travel without scattering. So what exactly are nanowires and quantum wires? Nanowires are typically defined by their incredibly small diameter on the order of 1 to 100 millimeters and high aspect ratio, length much greater than diameter. They can be made from a wide range of materials, metals like gold and silver, semiconductors like silicon and gallium arsenide, or even oxides and polymers. Quantum wires are a more specific class of nanowires where quantum effects dominate electron behavior, especially at cryogenic temperatures or in materials with exceptionally clean and defect-free structures. One of the most exciting properties of these 1D materials is their tunable electronic and optical behavior. For example, in semiconductor nanowires, simply changing the diameter can shift the band gap, altering how the material absorbs and emits light. This allows for customizable photonic devices such as lasers, LEDs, and solar cells tailored for a specific wavelength. Moreover, nanowires often exhibit high surface-to-volume ratios, making them exceptionally sensitive to environmental changes, ideal for chemical and biological sensors that can detect molecules in ultra-low concentrations. Want to build faster transistors? Nanowires can help. Their confined geometry allows for high-speed electron transport, and their small size fits perfectly into the ongoing trend of miniaturizing electronic components. Some of the latest field effect transistors, FETs, are already being built using silicon nanowires, showing promise for extending Moore's law even further. In the realm of quantum computing, quantum wires made from topological materials are being explored to host Majorana fermions, exotic particles that could form the building blocks of fault-tolerant qubits. Another fascinating application lies in energy harvesting and storage. Thermoelectric nanowires can convert heat into electricity with greater efficiency than their bulk counterparts due to enhanced phonon scattering and altered electronic transport. Similarly, nanowires are being incorporated into next-generation batteries and supercapacitors, where their high surface area boosts charge storage capacity and accelerates charge-discharge cycles. But how are these tiny structures made? Techniques like chemical vapor deposition, CVD, electrochemical deposition, and template-assisted growth are commonly used to fabricate nanowires with precise dimensions and compositions. For quantum wires, even more refined methods, such as molecular beam epitaxy, MBE, are used to achieve ultra-clean interfaces and atomic-level control. Of course, working with 1D materials comes with challenges. Their small size makes them difficult to handle, integrate, and characterize. Maintaining consistent quality across large batches is still a hurdle, and their quantum behavior can be easily disrupted by defects or environmental noise. Nevertheless, researchers are making rapid progress, especially as tools like scanning, tunneling microscopy, STM, and electron holography offer better ways to study and manipulate these structures at the atomic scale. So, why are scientists and engineers so excited about nanowires and quantum wires? Because they offer a unique playground where quantum mechanics meets engineering, opening doors to technologies that were once confined to science fiction. From ultrasensitive biosensors that can diagnose disease at the molecular level to quantum wires that may one day form the backbone of quantum internet, the potential of 1D materials is vast and still unfolding. Could these tiny wires hold the key to the next technological revolution? Many believe they might, and as our tools to see and shape the nano world continue to improve, the possibilities for discovery and for innovation only grow. One-dimensional 1D materials such as nanowires and quantum wires are structures with nanometer scale diameters and lengths orders of magnitude greater, resulting in quantum confinement in 2 dimensions that gives rise to electronic, optical, and mechanical properties drastically different from bulk materials due to size effects and a high surface to volume ratio. For example, silicon nanowires show size-dependent band gap widening when diameters shrink below 10 ME, and it's like forcing electrons to march single file down a narrow hallway. They behave very differently than in an open room. Nanowires can be synthesized via top-down methods, e.g., lithography and etching, or bottom-up approaches, e.g., vapor, liquid, solid growth, with precise control over composition, diameter, length, and crystallinity, enabling incorporation of dopants and heterostructures during growth, but presenting challenges in alignment, uniformity, and scalability for device integration. For example, gold-catalyzed VLS growth of gallium arsenide nanowires is widely used in nanophotonics due to excellent orientation and defect control, and it's like growing crystalline icicles with customized flavors and colors, shaped from vapor as they solidify into slender rods. Quantum confinement in 2 dimensions produces discrete transverse energy levels and a 1-dimensional density of states with Van Hove singularities, leading to sharp changes in optical absorption and emission and highly diameter-sensitive transport characteristics such as conductance and effective mass. For example, CDC quantum wires exhibit photoluminescence peaks that shift with wire diameter due to quantized energy levels. And it's like tuning a guitar string. Shortening or tightening it changes the pitch, just as narrowing a quantum wire tunes its electronic response. In sufficiently pure and short quantum wires, electrons can travel ballistically without scattering, yielding quantized conductance steps and ultrafast transport where resistance arises only at contacts rather than within the wire, a phenomenon first observed in gas/algas quantum point contacts as integer multiples of 2e2/h. It's like a frictionless water slide. Once the electron starts moving, it glides unimpeded to the end. Nanowires exhibit exceptional mechanical strength and flexibility due to their crystalline, defect-limited geometry, and their thermal conductivity can be tuned by manipulating surface roughness, phonon confinement, and wire orientation, enhancing or reducing heat transport as needed for nanoelectromechanical systems and thermoelectric devices. For example, silicon nanowires with rough surfaces show reduced thermal conductivity, improving thermoelectric efficiency via phonons. And it's like making spaghetti out of diamond. Strong, flexible, and capable of transporting heat and stress in surprising ways. Semiconducting nanowires form the basis of ultra-small electronics, fabricating field effect transistors, logic gates, and memory elements with low power operation, high sensitivity, and dense integration through gated structures that precisely modulate current and heterojunctions that tune barriers and contacts. For example, silicon nanowire FETs are being explored for sub-5 nm CMOS technology as alternatives to FinFETs, and it's like shrinking an entire electrical switchboard into a single intelligent thread that reacts to the faintest control signals. Quantum wires with direct band gaps excel in optoelectronic applications, lasers, LEDs, solar cells, and photodetectors, thanks to efficient light absorption/emission, polarized emission, and nanoscale wave guiding, with nanowire arrays enhancing light trapping via resonant and scattering effects. For example, GaN nanowire LEDs produce bright, coherent light with reduced heat loss and improved efficiency, and it's like training fireflies to line up and blink in perfect unison, each one tiny, but together forming a luminous signal. The high surface to volume ratio of nanowires makes them extremely sensitive sensors for chemical, biological, and gas detection, enabling single molecule sensitivity through surface functionalization without disrupting cellular function. For example, silicon nanowire sensors functionalized with antibodies detect cancer biomarkers at femtomolar concentrations, and it's like placing an ultra-sensitive antenna in a crowded room that can pick up a whisper from across the hall. One-dimensional materials are poised to drive future quantum devices and integrated nanosystems. Hybridizing nanowires with superconductors or topological insulators to explore Majorana fermions and quantum entanglement, contingent on scalable synthesis, defect control, and reliable circuit interfacing. For example, NSB nanowires proximatized with superconductors have shown signatures of Majorana bound states as candidates for topological qubits. And it's like weaving quantum logic into threads of light and electricity, paving paths toward computation at the edge of physical law.